Hello, and welcome back to Introduction to Genetics and Evolution. In the previous video, we talked about basic single gene inheritance, or basic Mendelian inheritance. It's called this because this was elaborated first by Austrian monk Gregor Mendel. We saw how you get single copies of genes or alleles from one parent combined with single copies of genes or alleles from another parent. In this video, we'll talk about a special case of inheritance, that of X-linked inheritance. What happens when genes are on the X chromosome that some of you may have heard of? The other thing we'll talk about is following what happens with multiple genes. This is something we'll be doing quite a bit later in the course, but we'll begin that now looking at the principle of independent assortment. This is something that was also elaborated by Austrian monk Gregor Mendel. Now, some chromosomes have slightly different patterns of inheritance from what I described previously in terms of the single copy from males, single copy from females going to offspring. And this was first hypothesized partially because there are some hereditary diseases that pop up much more frequently in males than in females. And this is true even when both sexes are likely to get the disease. That you just see a lot more men having it than women having it. There are some cases of muscular dystrophy, for example, which fit this description. Now, Drosophila geneticist Thomas Hunt Morgan studied this around the turn of the 20th century. He was working with fruit flies, and specifically working with a white-eyed mutant fly. He found that inheritance was sometimes different depending on the sex of individual. That if you tracked what was happening with particular genes in males versus in females, you're getting completely different patterns. He inferred from this the principle of sex linkage, or X linkage. We now know that there are some genes that are actually not present in two copies in all organisms. That quite often you'll find that in humans, males may have one copy of a gene, and females may actually have two copies. And these are genes that are on what's referred to as the X chromosome. So often across species, males are XY. So they have one copy of the X chromosome, and instead of having a second copy, they have this other chromosome called Y. Whereas females have two copies, so females are called XX. You've probably heard this before. Now, there's not the same set of genes on the X as on the Y, despite the fact these two chromosomes pair and separate. And you'll see the principle using them is very similar to what we discussed before, except that the X has one set of genes and the Y often has a different set, and in fact, often has very few functions. In humans, one of the few genes on the Y chromosome is a gene which basically makes the embryo become a male. Now again, in this case, you get different patterns of inheritance depending on who is the mom, who is the dad, and whether you're looking at male or female offspring from them. Now I mentioned muscular dystrophy. Another example is green color blindness. Now this is an X-linked recessive in humans, meaning that if you're a female and you have two copies of this particular mutation, then you will be colorblind. Males only get one because it's on the X chromosome. So if they have the one copy, they are colorblind. This picture on the screen depicts what somebody with green color blindness may actually see when you're looking at the picture. So in the picture on the left, it has the number 74 very clearly visible. In the picture on the right, if you're green colorblind, you actually won't see the 74. In fact, you may see a different number in there. Now, inheritance of genes on the X chromosome can be studied very similarly to what we described, and again, using the Punnett square, just like what we did before. And what happens in this case is you just insert a Y instead of the second allele that would go into males. So let's try this now. Let's imagine that you're studying red-green color blindness. Something that I just mentioned is something that's inherited on the X chromosome. Well, let's say hypothetically that you have a male which is red-green colorblind. So here he is. Here's his X chromosome, and I'll put a little RCB on there for red-green colorblind. For the female, let's say that she is just normal. She does not have this mutation. Just has two regular X's. So we can follow what happens in this case just like what we did before. So again, the male is equally likely to either give this X, which has the mutation, or the Y. I've already drawn in the Y's there for him. So here, let's put this in. Here's the male's X, RCB, X, RCB. Okay. And the female will always give her just regular X, regular X, regular X, regular X. Now what do we see here? The male offspring are the two on the bottom because those are the ones that have the Y chromosome. You don't become a male unless you have a Y chromosome. Okay, so this is true in humans. It's not true in all species. So looking at these individuals on the bottom, would they be red-green colorblind or no? So look at it carefully. There is no red-green colorblind mutation on them, right? So the two males here would be just fine. We can write the word fine here. What about the females? Well, the females do get the red-green colorblind mutation, but I mentioned it's recessive. So they have one normal copy and one sort of broken copy. So in this case, again, the females would also be fine. Well, that was interesting. Well, let's try something a little bit different. Let's switch it around. This time, let's say the mom was red-green colorblind and the dad had perfect vision. Okay, so this case here is dad. He's got just a regular X. Mom's got X, the RCB mutation. X with the RCB mutation. Okay, so let's follow patterns of inheritance. Again, the dad's always giving the Y. In this case, he's giving an X. Okay. The mom is always giving an X RCB. X. So now what do we see? Well, let's look first at the girls. So the girls are the two X's. So they have one normal X chromosome and one with the mutation for red-green colorblind. So again, the daughters in this case would be fine. So this is similar to what we saw last time. However, look at the boys. The only X chromosome the boys have has this mutation. So in fact, the boys are actually red-green colorblind. So we see a different pattern of inheritance in this case, depending on whether you're looking at the daughters or the sons, and depending on who is the mom and who is the dad. Okay? So this illustrates some principles of X-linked. Now let's look a little bit more broadly in the genome. Now everything we've focused on so far has been looking at single genes in isolation. But the genome is a very big place. The human genome, for example, has on the order of 23,000 protein coding genes. These are genes that actually make protein. It has many other important things in there. There are other things that affect how much of a protein are made, et cetera. These are called regulatory regions, et cetera. Now, again, we have 23 pairs of chromosomes, one pair being that X and Y, the other pairs being ones that follow just regular Mendelian inheritance, as we described before. Now, interestingly, so you see all these 23 pairs of chromosomes in the picture on the bottom left here. They're actually all inherited independently. So let's say, for example, I get, a particular chromosome. I have a particular chromosome 2 from my dad, a particular chromosome 2 from my mom. I have a particular chromosome 3 from my dad, a particular chromosome 3 from my mom. If I give to my daughter my dad's chromosome 2, there is no way that you can know which copy of my chromosome 3 I'm going to be giving. I'm equally likely to give my dad's or my mom's chromosome 3. But basically, what's happening with one chromosome is independent of what's happening on these other chromosomes. You're not more likely to give both your dad's copies or both your mom's copies when you're looking at different chromosomes. This is referred to as Mendel's law of independent assortment. So what happens when you're studying two traits that are inherited from genes on different chromosomes? Well, let's look at two traits. In this case, I'm looking at two that show patterns similar to being single gene inheritance. They're not actually inherited through single genes. One of them is what happens when you put your hands together like this. Watch. Put your hands together like that and see which thumb is on top. In my case, my right thumb is on top. For a lot of people, the left thumb is on top. For a long time, people thought this was inherited as a single gene. That actually probably isn't true, but just pretend that's the case for right now. If you study the inheritance of this, it looks like the left thumb on top one is dominant. The right thumb on top is recessive. The other trait we'll look at is again, dealing with thumbs, because they're easy to show, is straight thumb, which sort of looks like this, or hitchhiker's thumb, which is, mine is definitely much more hitchhiker, where it comes really far back. Well, it's thought that straight thumb is dominant, so I have both recessive things in this case, whereas the hitchhiker thumb is recessive. So let's say you were following these two traits together. Let's say you're following inheritance of them. Well, let's do a hypothetical example. Let's say that you have a dad who has left thumb on top and straight thumb, having kids with a mom that has right thumb on top and hitchhiker. So let's call them, just using these letters here to make it a little bit easier to follow. Big T, big S, crossed with little t, little s, little s. Okay. So in this case, this is referring to straight versus hitchhiker for the S, and left versus right with the T's, where capital T is a left. Okay. So let's follow what happens. Well, the offspring will obviously get one big T, one little t, one big S, one little s, right? Because there's no alternative. So here we go. Here's the kids. Big T, big S, little s. And let's say the kids marry each other and have kids. It's a little gross, I'm sorry, but let's pretend this just for a moment. What will we see in their offspring? Well, the kids can give different alleles, right? This boy right here could give his big T or he could give his little t. He could give his big S or he could give his little s. And the same thing is happening with the girl here. So it's a little bit more complicated what's going to happen. These T and S alleles are going to be inherited independently from the parents. But again, if you give the big T, you're not more or less likely to give the big S or the little s. So there, I showed here on this picture 4 possible gametes. Big T, big S, big T, little s, little t, big S, and little t, little s. Those are the 4 possible gametes you can give. Now, there's 2 ways you could try to predict what the offspring would be like. The better way, which I'll show you second, is to actually multiply probabilities. We'll come back to that in just a moment. The other thing you can do, which is maybe more intuitive but definitely more laborious, is to follow what's happening with all the gametes. Work out all 16 possibilities. So let's do that one first. I won't do the whole thing, but I'll just show you how it would go. So again, here's the thing. We can fill this in. Remember, all 4 possible gametes we have are big T, big S, big T, little s, little t, big S, little t, little s. So that's true for one of these. Let's do the other one. Big T, big T, little s, little t, big S, T, little s. And you can follow what's going to happen with each of these things. So in this case, mom will always be giving a big T and always be giving a big S. Dad will be giving a big T and will be giving a big S. So there's one individual. Now this is going to take forever if I do this. So let me just fill in what all the answers would be. Boom. So here's all the possible outcomes there. And I have here up in the upper left corner a little cheat sheet so you can see what happens in terms of what they would look like or their phenotype. That if you have a big T, you got your left thumb on top. If you have a big S, then you're straight rather than hitchhiker. So let's look at the ratio here. How many individuals would be left and straight? Remember, left and straight are both dominant. Well, let's count them. This one, this one, this one, this one, this one, this one. Am I missing some? This one. T and big. Oh, there's one. There's one. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 that are dominant for both. Okay. How many would be right straight? Right thumb on top straight. So in this case, color. Right thumb on top straight would be little t but big S. So little t but big S would be this one, this one, there, those 3. Okay, so we have 3 that are dominant for one, recessive for the other. The opposite would also be 3. This would be what happened if you're left thumb on top but hitchhiker. That would be these 3 over here. I'll put X's this time. So again, 3 for when you have one dominant and one recessive. And finally, 1 that's the double recessive. So the ratio you get is 9 to 3 to 3 to 1. So again, there's 16 possible outcomes here. And this is the ratio we expected. That was laborious. So let's see how we can do this a little bit more straightforwardly. Well, there's a very simple thing you can use from basic probability that if you have 2 independent events, all you have to do is to multiply the probabilities for the joint probability. Just like if you're flipping a coin. What are the odds you flip a coin and get heads twice? Well, the odds of you flipping a coin and getting heads the first time is 1/2. Odds of you flipping it a second time and getting heads is also 1/2, so it would be 1/4. Well, we can apply this same principle to this problem. Here's all the possible outcomes when you're looking at just one gene in isolation. So we have here, this is what we'd see if we were just looking at what's happening with the T gene, the one that controls left versus right thumb on top. These are the 4 possibilities when you're looking at hitchhiker versus straight thumb. So all we have to do is just multiply the probabilities to get these different genotypes. So we say big T, big S, that would be 1/16, right? Big T, big S, little s, that would be 1/4 times 1/2. The half is a quarter, so this would be, in this case, 1/8. We can fill in this whole thing. There we go. We filled them all in. Now, if we do the same thing, let's add which ones would be left them on top straight. Well, we can just add them up. We can do it, let's do it by 16th, so it's a little bit clearer. So there's 1 here. This would be plus another 2, because 1/8 is 2/16, right? So this would be 3. So 1 plus 2 is 3. Plus 2 is 5. In this case, plus 4 is 9. So again, we have 9/16 have left thumb straight. So again, if you do this whole thing, it becomes 9/16, 3/16, 3/16, and the last one over here being the 1/16. We get that same overall ratio, and this time we can do it just by multiplying probability. So let me give you one to try on your own, and then I'll give you a problem at the end of it. So again, assume independent assortment between A and B genes, okay? What will the genotypes and proportions be of the offspring if you're looking at big A, big B, little b? So this is the double heterozygote again, crossed with big A, little b, little b. This is a little bit different in this case. So what I suggest to you to do is to multiply the probabilities. So look at what's happening just with the A gene, and look at what's happening just with the B gene, and multiply those probabilities together. Let me give you a moment to try this out, and then just solve this problem.